So we have a problem here that exploits Bernoulli's principle on one of nature's best fluid dynamicists, the prairie dog. So as we look at this, prairie dogs are, I don't think we have them around here, they're a varmint out in the Midwest and the Great Plains, and they will dig holes and they live in tunnels underneath the ground. They wreck crops, which is why they're a varmint. Now, typically if you just have these holes there, there would be no airflow and they would all suffocate. But prairie dog mounds actually have a natural air exchanger put into them because they have the hill raised at one side, and that causes a pressure difference that causes fluid to move through the hill, or excuse me, through the tunnel. So let's take a look at this one. Let's assume that at the entrance, that at point 1, my velocity is 6 meters per second. And so that's the wind blowing right there. And let's assume the velocity at 2, the velocity over the top of the mound is 7% faster. So that'd be 1.07 times 6 meters per second. And so what we want to find is what is the pressure difference between point 1 and point 2. Okay, so basically the way that we're going to solve this is we're going to use Bernoulli's equation and take a look at the pressures at point 1 and point 2. First thing that we need to do is we need to make some assumptions. I don't know why this keeps switching back and forth today. So my first assumption is I'm going to have a streamline. But I see no streamline in the picture. Well, I know that there's airflow here that's going to here, so I'm just going to assume there has to be a streamline between those 2 points. So I'm just going to draw it in. I'm also going to assume steady flow. There's nothing in this that says otherwise. I'm going to assume it's an inviscid flow. Friction, there's not really a lot of friction in air as it rubs against each other. And the last one is I'm assuming compressible flow, so density is constant. I can make that assumption because the airflow is flowing slow enough. Well, so what do? Well, I'm just going to write Bernoulli's equation at the 2 different points. So at point 1, it's pressure 1 plus gamma over 2 V1 squared plus Z1 times gamma of the fluid. That's got to be constant along the streamline. Well, point 2 is also on the streamline, so it has to equal the same thing. So pressure plus gamma over 2 V2 squared plus Z2 gamma. Now, as we're looking at that, point 1 and point 2 are basically the same height. So if we assume that Z1 is equal to Z2, or Z1 is basically equal to Z2, those terms will be the same and they'll end up dropping off. And so then I can rearrange this equation, pressure 1 minus pressure 2, get the pressures all on one side, and then we'll get the velocities all on the other. So rho over 2 times V2 squared minus V1 squared. And at this point, we just plug in the numbers. So we have to look up density of air, typical density of air at standard temperature and pressure is 1.23 kilograms per cubic meter. We can go look that up in our book. And then we're going to multiply that by V2 squared. So 1.07 times 6 meters per second squared. I'm going to erase our assumptions here just to give us a little bit more room. So let's clean up that spot there. So I have that, need one more set of brackets, minus 6 meters per second squared. And then when I plug in all the numbers, let's take a look at what my units are going to be. I'm going to have kilograms per cubic meter here. I'm going to have meters squared per second squared from this part here. So when I jam those two together, I'm going to cancel out. Kilogram meter per second squared is going to give me a Newton, and then I'll be left with square meters. So 3.21 newtons per meter squared, or 3.21 pascals. And so that's the pressure difference between 0.1 and 0.2, and that causes a slight breeze through the hole. And also realize 3.21 pascals is not very big, because that's 3 newtons per square meter. That's like 3/4 pound patties over a 3 meter spot. So not a lot of pressure, but enough to keep the little guys alive.